Good afternoon, everyone, and thanks again to join session on different optimization techniques with MATLAB. So, in this session, we'll see what kind of different optimization techniques are available in MATLAB. Okay. So, first of all, we'll start at what is optimization. Then we'll see some one case study. Then further, we'll see that what kind of different local optimization and global optimization functions and algorithms are available in MATLAB. What is optimization? Optimization is an iterative process by which a desired solution, like maxima, minima of the problem, can be found while satisfying all its constraint or bounded conditions. So what we do here? We create some kind of objective functions and we provide some boundary conditions. Based on that boundary conditions and some equalities, inequalities, we try to optimize that objective function within that given boundary conditions and equalities or inequalities are there. So in MATLAB we can do a linear optimization, linear equations if you have, or non-linear optimizations, or mixed integer type optimizations. So why optimization is required, right? That is very important to know that why optimization is required. So lots of applications are there based on the optimization. Let's say that a salesperson has to visit around 100 shops in a day, but the problem is that he doesn't know what optimized path he will follow so he can visit in every shop in a day. So we create some kind of optimization objectives and we optimize the path, and minimum path will be optimized, and we can extract the minimum path. He will follow that path and he can visit all the shops in a day. Or some other examples, like let's say you have some plant, and let's say that you have some chemical plants, and you are making some products based on the chemical plants, and you require to know what will be optimized chemical values so cost of the plant will be minimized, right? Some other applications, like let's say that I have to fly a drone, and the drone had to visit from source to destination, of course, and there are some wind speed also. Wind is also there. Wind, let's say wind is flowing there. So what will be a optimized path for that drone that it can go in a short duration from source to destination? What will be a optimal path for that, right? So this kind of applications, for this kind of applications we require optimization techniques for that. Okay, just one minute. Okay, there are two kind of optimization in MATLAB, that is local and global optima. If you have to find, depends on you. So sometimes you know that why didn't the solver find the smallest minimum? There is the reason behind that. There is not a single algorithm which can find out the exact minima and maxima. So here, which you see here right now, this is the, let's say this is the curve, and you see that this is the local minima, right? This one, and this is the global minimum in this case. So let's say that my start point is somewhere here. If I'm saying my start point is somewhere here, when I start the optimization, what it will do, that it will find out the near somewhere some minimum value, that is the local minimum. It will not move to the global minimum. So it depends that what is your boundary condition and what is the start point. If my start point is somewhere here, then it will able to find out the global minimum. So we have to careful regarding this to find out the global maxima and minima while we are doing this. Generally, optimization toolbox which is available in MATLAB is solvers find a local optimum. This local optimum can be a global optimum as well. Depends that what is your start point, what is your boundary conditions. They find the optimum in the basin of attraction of the start point. Another module which we have, that is global optimization toolbox. In global optimization, advanced algorithms are available, like particle sum, pattern search, simulate an annealing based on that algorithm which we have here. So different advanced algorithms are available there. Genetic algorithms is also available there. So depends on you that are you going for the local minima or global minima or maxima. Based on that you can choose your algorithms. These are the basin of attractions here which you see. One dimension basin of attractions we define like this. So let's say that my point somewhere, my start point is here somewhere. So this is the minima here. So if my point is in this region, this basin of attraction, then it will find out the this maxima, or if it is in this region, then it will find out this minima. But what if my point is in this region, then it will find out the this minima, not this one. So depends again that what kind of boundary conditions are you providing and where is your start point. Okay, several basin of attractions can be like this, and you can start from multi points. So it will start finding the minimum value from multi points, or you can provide some constraints like this, and you can reduce further the region basin of attraction where you don't require a minimum or maximum value. So that's why we provide some boundary conditions like this. These are the optimization types in MATLAB. Optimization types are two ways you can design your objective in MATLAB. First is problem based optimization. Second is solver based. So there is not such a rules to select which one you are going to select. Depends on you that in which you are feeling easy, go for that. So I will show you both one, problem based also and solver based optimization techniques in MATLAB. So basically solver based and problem based optimizations are there. So here nonlinear optimization, linear programming and mixed integer linear programming optimization we can do. Quadratic programming, least square methods also we can use a system of nonlinear equations. If I have to solve the system of nonlinear equation, that also optimization we can do. If I am talking about global optimization, we have advanced algorithm like genetic algorithms, particle swarm, surrogate optimization, simulated annealing, multi-objective optimizations are available there. These are the functions in a single line command we can optimize our objective functions. So problem based is easier to create and debug. So depends again that in which you feel easier, you can go for that. So it is easier to create and debug only for linear or quadratic problems with linear or integer constraints. So if you have a quadratic problems or linear equations, if you want to optimize, you can go for the problem based. Represent the objective and constraint symbolically. So in problem based we create symbols of our parameters, means the parameters which we have to optimize. Solution time is longer because of translation time from problem form to matrix form. So in problem based it takes a little time. If you have a big objective, and in that case it will take time. Why it will take time? Because the symbols which we create of our parameters, I mean the parameters which we have to optimize, it takes time to convert from symbolic to matrix form. You can apply problem based in linear programming problems, mixed integer linear programming problems, quadratic programming problems, and linear least square problems. So in this case you can go for the problem based optimization. It is easy to design, but it takes time. Solver based optimization you can use for linear and non-linear both. We represent the objective and constraints as a function or matrices. So always remember, when you are going to choose solver based, then whatever parameters we have, the coefficients of parameters, we represent it as a matrix. So it takes a short time because it is already converted as a matrix. So we don't require to convert as a matrix in MATLAB. Okay. Solution time is shorter because of there is no translation time to convert in the matrix form. This is the goal which we are going to optimize. This is a one case study. The variables and expressions in this problem represent a model of operating a chemical plant. from an example in Azure and Himmel below. They created this whole algorithm to optimize their plants. So what we have here, what is the objective which we have here, which you see, this is my objective function here. This is a linear equation, right? So this is the cost of the plant. So what we have to do, we have to minimize this cost function, this objective function which we have. So for this, what will be a chemical parameters value, so the cost will be minimized of my plant. Okay, so there are around 16 to 18 parameters which we have to optimize in this case. Okay, so these are the steps which we are going to follow. First, which get an overall idea of the problem, identify the goal of maximizing or minimizing, identify variables, identify constraints. Constraints can be linear and non-linear. Determine which variables you can control, then specify all quantities in mathematical notation, check the model for completeness and correctness. Okay. So I am going to switch here in MATLAB. So first of all, we are going to start from linear and problem based. Okay, here I have this objective function which you see here. This one is the objective function. Constraints are like this. Linear constraints are there. These are the boundary conditions. Fine. These are the boundary conditions. These are non-linear linear inequality. This is a linear equality. This is also a linear equality. So this I1, C1, I1, I2, HE1 which you see, that are the chemical variables. Okay, these are the chemical variables. We have lots of equalities and inequalities. So total around 18 parameters we have, that chemical values which we have. So first of all, in problem based, we start like this. First of all, we create symbolic variables. So we use inbuilt function in MATLAB that is called optimver. Let's say that you are not aware about optimver. Just select this, right click, and directly you can go in help from here. You can open this variable in a browser like this. Okay, so here is the explanation. What kind of syntax are you going to use, right? And if I scroll below, you will get some examples also, that how optimver works. So you see that whatever parameters you have, we create a variable, variable for that. So here we provide the lower bound, upper bound with the parameter name. So in some cases we will not have a upper bound, just provide the lower bound. So this is the chemical values, it cannot be negative, so always lower bound will start from the 0. Maybe in some cases you will have negative values also, so you can provide the negative values also there. So if you have both, you can provide like this in optimver. So nothing you have to do, just simply you have to create like this, whatever we have. So in this case we have 16 parameters, and first step is that we have to create the symbolic of that and lower and upper bound from that. Okay, after creating this, we create our problem. So we use this inbuilt function optim problem. Hope that you got how to create this using optimver. Okay, optim problem, this is the parameter objective. What is our objective? That plant equation to minimize the cost. Okay, so this is the objective over here. Now we define the equality constraints here, inequalities and equalities. So we have 3 inequalities here, right? So one thing is very important here, that is fine, these are the inequalities. So here we created a lean proc as a structure. Let me execute this first of all. So you see that a structure will be created here as a system object, as a lean proc. Here, okay. This is the linear problem which we have to optimize it. So here we have created as a structure. In the same structure, we are going to add these constraints. So you see, lean proc dot constraints dot first inequality, then second one as it is, you can write it, then third one. Three only we provided. Now next, let me execute this first. Next, what we are going to do, we are going to add equalities. So how many equalities we have here? 8 equalities we have. We will add again in the same structure, lean proc dot constraints, and this is the variable, econs 1, econs 2 and 3, like this till 8. So as it is, whatever you have equalities, as it is, you have to write it here using this operator. Okay, so once we have this, we solve this. Simple. So you see that how easy it is to optimize this plant, right? First of all, whatever parameters we had, we provided a lower and upper bound for that. Second step was we created a optim problem, is the function which we have to optimize, that is the objective function here. And for that, what will be the parameters value for that? Once we have created all this, we use the solve function. Solve of what? That lean proc this object which we created. Just we have to give this command and we'll get the output here. So it is started solving. It will take a little time because lots of iterations will be running. So you see that it says that optimal solution is found, and for the optimal solution means for the minimum value, what will be your parameters value? Like first chemical should be 0, second chemical should be 0, C will be this and this, in a single line, very short duration. Just we use and we got the parameters value in this case, right? Perfect. Okay, once we have this, next what will be a minimum value in this parameters value? So simply we use lean proc dot objective, because in lean proc we have an objective function. See here, lean proc dot objective means we are going to put this all these values here in this function. Okay, so lean proc evaluate lean proc dot objective and the solution which we got from here. That's all. Let me execute this, and here you see that minimum cost will be, that is 1.27027 and this some values into 10 to the power 3. Perfect. So this is the way how we can use problem based. So just 4-5 sections we used here. We create, let me summarize that. First of all, whatever variables we have to provide the lower and upper bound for that. Then second step is we have to create a problem which we have to optimize. Okay, one thing more here, as a default MATLAB always identify the minimum value. Let's say that if you want a maximum value, so you have to multiply with minus sign in this objective function. That's all. If you want a maximum value, you have to multiply with the -1 in this objective function. That's all which you have to do, and everything will be same. Next, we created constraints. We added a constraint in this system object, this object which we created, right? So 3 inequalities we had added here like this. Next, equalities we added here. We had 8 equalities. So this is the way how we add it. Then in a single line, just give the command solve and it will be solved here. That's all. And execute that, what will be a minimum value, evaluate, and this objective function with this solution which we got from here. That's all. This is the first thing which we can do here. I'm going to close this. I'm going to switch here again. Second is solver based. In solver based, how we solve our objectives. So like this, we have to create our equations. Ax is smaller than b. So always if you have linear inequalities, if it is greater than, multiply with minus and make it as a smaller than, you for first thing. Second, whatever coefficients are there of right side and left side, you have to convert it as a matrix. As I told, in the solver based we convert as a matrix, so it takes less time. We have to create a matrix for lower and upper bound also. Then we use, if it is a linear programming, then we use a leanprog function. A is the matrix of left side inequalities, B is the matrix of right side inequalities, means the coefficients of that. Then A equivalent is a coefficients of left side equalities. B equals the right side coefficients of equalities. Then lower bound matrix and upper bound matrix. How it work? Like this. In this case, you see objective function. So when you convert this objective function in a matrix, it will be 1 and 1.5, right? Now in this case, this is the inequalities. What will be a matrix in this case? 1 1, because coefficients of x1 x2 is 1 1, right? So 1 and 1, and second row will be 0.25 and 0.25. What will be B? Right side 150 and 50, right? And this is a low, we don't have a lower bound here. No, we have a lower bound as well. So lower bound will be 0 0 matrix, and upper bound will be 50 and 25. So very simple. If you don't know how to create a matrix, simply like this you can create. So check in this one, that is 1 1 and 0.25 0.5, right? So 1 1 semicolon means this is the first row, semicolon, then we are going to write second row 0.25 and 0.50. So this will be a like this, right? If you have to create a B, that is 150 and 50. So your B will be like this, 150 and 50. Sorry, it will be as a column semicolon and 50. We have B also here. Now we have lower and upper bound. Let's say lower bound is here 0 0, perfect. Upper bound is here, it is given, that is 50 and 25, 50 and 50 semicolon 25. So we have all these values. A we have, B we have, lower bound we have upper bound. We don't have equalities, so we are going to leave it as a blank. And the objective function, so here the coefficient of objective function is 1 and 1.5, right? So let's say objective function is this. Objective function, that is 1 and 1.5, 1 and 1.5. That's all which we have to do. Now to solve this, we use leanprog. We will get the x1 x2 value here, and output will be as a f eval. Let me write like this, and leanprog, and here you have to provide all these parameters. So first of all, we have a function. Function name is as a obj. Then a and b, a b. We see that we don't have equalities, so we are going to provide it as a blank. Now you see we have to provide the lower bound and upper bound. So lower bound is L and upper bound I defined in a U. Bracket close and enter this. Okay, here I had not to use the square bracket, by mistake I used it. Now you see that what it shows, the x1 x2 value is 0, and for that equation the minimum value is also 0. Perfect. So let me show you again what we have done right now. First of all, we defined the objective function. Objective function is this. What is objective function? Coefficients of your linear equation, 1 and 1.5. Perfect. Then a, left hand side, so two inequalities we have, so we created a matrix for that, something like that. Here first row 1 1, that's the first linear inequality, and the second inequality coefficients. Same way we define the B. Then we don't have equalities, we left it as a blank. You see here we left it as a blank, right? This is the blank here. And lower bound as a L, and upper bound we have provided like that. In this case you saw we had two parameters, that is called x1 and x2. So we had to find out the optimized value of x1 x2, and what is the solution, I mean what is the minimum value of this objective function, this one. Perfect. Okay, the same chemical plant, if I have to use as a solver problem, then how we can solve using the solver based. So I have all this inequalities, equalities, lower and upper bound. So we have to use the strategy. So in this case what we are doing, we are let me clear everything, then we'll run it again. So depends on you that how you are going to create. What I am doing here, I created for all parameters as an index name. BF1 is at 8, C is 7, AP is 16. Just a number of parameters, number of integer values for that. For first one, then second till 16. The first step which I did, because it's the big problem. That's why we have a 16 parameter. That's why we are doing like this. Otherwise you can do directly like I did before. Okay, now we have a lower and upper bound. So we have to create a matrix like before. So what I am doing here, I creating a one dump of 0. So simply if you give this zeros 1 to 16, it will create a 0 0 matrix. So in this case, in some cases we don't have lower bound. That's why we are creating one zeros, and here is the lower bound for that. Whatever lower bounds are here, we are providing. So in some cases lower bounds are 0. So let me run this and show you that what is this LB. Here you see, so for some parameters lower bounds are 0, for some parameters lower bounds are this, means that the chemical value, that minimum I require this much. In other cases the chemical values can be 0 as well. Okay, so this is a strategy that how we are writing if you have a big objective, big problem if you have to solve. Same for the inequalities, upper bound, sorry, this is the upper bound. Same way we are going to provide. So what we are doing, we are creating, see, in some cases upper bounds are not mentioned, so it can be infinity also. So in this case we are creating a dump matrix of infinity. Simply INF 1 to 16, it will create an infinity. So what we are doing, we are masking at index P1, P2, I1, whatever values we have assigned there, it will take the index from there, and this value will be assigned on that specific index. So again I am executing, and let me show you this upper bound. I am switching here. Upper bound is here. So wherever we don't have upper bound, we assumed as an infinity, and remainings are index on the value which are given there. Perfect. Okay, I am switching here again. Write linear inequalities. The same way we are providing the inequalities also. We are creating 3 inequalities we have. So 3 rows and 16 columns, right? And wherever values we have of inequalities, we are providing that values here. So when I run this, you can provide it manually also, but it will take a little time. So you see that of left side of inequalities, we have like this. Wherever we don't have variable, you see here in this case, if I scroll up inequalities, in this one you see that other 16 parameters we have, but 2 parameters we are seeing only in this case. So it means remaining have a 0 coefficients, right? So same here, wherever we don't have parameters, it means it has a 0 coefficient. So we replace it as a 0, right? Okay, we created a matrix for inequalities. Okay, till here. Then equalities also the same way you can create a dump. 8 equalities we have, so 8 into 16, 8 rows and 16 columns in this case, and just put the value whatever in a parameter coefficients you have like this, so it will be replaced by that. Perfect. Now about the objective function. So let me jump there. Objective function above, you see that in this objective function we have 3 parameters only. It means remaining parameters have a 0 coefficients, but if I am using solver based, we have to define that 0 coefficients parameters as well. So always remember, so you see that how whatever variables we have, we are creating the 0 of that, and whatever parameters coefficients we have of SPS, PP and EP, we are providing here. So when I execute this, and let me show you that function f. Here, so wherever we don't have parameters, it means coefficients are 0. Wherever we have parameters, we provided the coefficients for that. So we have this linear objective functions as well. Now to solve this, so what kind of algorithm are you going to use? First of all, we use the single line function that is called optim options. So in optim options, we provide a different kind of options for optimization. Okay, so when I open this in a browser, and see, there is written solver name. If I click on this, it will show me that what kind of solvers are available here. F mean con is there, different solvers are available there. Like in this case, we are using algorithm dual simplex method. So this is the option. Okay, once we created everything as a matrix, here we are creating as a matrix. In previous one, we are creating a simple symbolic of that. Okay, once we have optim options, this one which you see here, we use to in previous one we are using solve. Here we use leanproc function. Leanproc, this is the objective function which we created here. Right side matrix, left side matrix of inequalities, then equalities, lower bound, upper bound. In the last, we are providing this option which we created here. Once we run this, we will get the minimum value, that is x, and the minimum the optimized parameter values x and the minimum value. So you see these are the optimized parameters value, and what will be a minimum value of the function. This is the same output we got in the problem based also, and the same output we are getting the linear based. So if I compare both for this problem, I think problem based was easier, right? If you have less parameters, then go for the solver based. If you have so many parameters, then go for the problem based. Okay, I am going to close this. Let me show you something more, that how to get a help and what kind of functions are available there. So this is a part of optimization. Just I will click here in the question mark, and from here I will search where is the optimization. Here is the optimization, and I want to know what kind of functions are available in this optimization toolbox. Just I will click here in function, and you see that how to create variables and problems, and these are the functions here. If I click on any function, I will get the help and explanation, helps and explanations both. Perfect. Expressions, if I have to write constraints, if I have to write equation, I have to write, I will use these functions. Solving, we will use this. And you see nonlinear optimization, we are going to use this function. For solver based optimization, we are going to use these functions. Solver based nonlinear optimization, we are going to use these functions. For multi-objective functions, we are going to use this. So all we are going to see one by one. Okay, and if you click on any like if I am going to click here, so you see that we have a syntax, we have a descriptions, we have examples, what kind of input arguments we can give, that is also given, what kind of output arguments we are getting, that is also explained here. Fine. So whenever you using any function in MATLAB, just explore the document. That is very important. Explore the document, then start. I'm switching here. So we saw this linear programming, both in problem based and the solver based. This was a case study. Now we will see little bit easier, which is easily to understand. Okay, here we are going to see mixed integer linear programming and linear programming. So where are you going to use mixed integers? This is one more question, that where are you going to use mixed integer programming, right? So let's say that you have again a electrical circuit equation, right? And you have to estimate something from there. Let's say that resistance you have to estimate. What will be a optimized resistance value? So resistance value will be as an integer. It cannot be 100.5 or 100.6. And you have already resistance 100 ohm, 200 ohm, 30 ohm, 40 ohm, something like that. So it cannot be a discrete. So in that case, to find out the resistance value, in that case we use mixed integer linear programming kind of thing. So there will be a decimal, I mean continuous data also, and discrete also. Else you can use linear programming problems. Okay, so both we are going to see. That's a very easy, very simple, and very easy it is. Let's start from the linears. So these are the constraints which we have. We have two parameters, x1 and x2. These are the constraints of that. So you already know how to create a and b for that. So a will be coefficients of this. See here it is written 1 1 1 and 1 by 4, then 1 minus 1 minus 1 by 4. So here you see all are smaller than, as it is you have to create the A matrix, then B. And now you see, if I execute this, just wait a minute. We'll get the A and B. We have A, we have B in this case, right? Okay, now about equalities. We have only one equality. So coefficients are 1 and 1 by 4. So A equivalent will be 1 and 1 by 4, and the right side this is 1 by 2. So this is a solver based. Okay. So we have this one also. Now objective function, or objective function is minus 1 x1 minus 1 x2 by 3. So you see here minus 1 and minus 1 by 3. So we have this objective function also. And the same way lin proc, which we saw in the earlier one, and what we will get the value of x1 and x2. So this is the parameter, optimized parameter value of x1 x2, where this function will be a minimum. Perfect. Okay, let me switch again here. So next we are going to see mixed integer linear programming. Fine. So in this case, it is the same way, same thing we have to do in this case also. Only the thing is that which parameter is integer, you have to index it here. So we have here, you see x1, x2, x3, right? 3 parameters we have, and x3 is integer. So what see, it is written x3 is binary here, right? So we provided here number 3 parameter is as an integer. So here you have to assign as a 3. If 2 was as an integer, then instead of 3 you have to write 2. If x1 was an integer, then you have to provide the value 1 here. We have to minimize this. So how will you write? Minus 3, minus 2, minus 1 in a single matrix, minus 3, minus 2, minus 1. And we emphasize that third variable is integer, and these are lower bounds, and this is a inequality, and this is the equality. So we already know we have to create a matrix. This is for inequality. You see that coefficients of x1 is 1, x2 is 1, x3 is 1, and the b is 7. So you see that 1 1 1 and b is 7. and equalities 4 to 1 and 12. So you see 4 to 1 A equivalent and B equivalent is 12. Perfect. So far so good, no issue. I hope that you don't have any doubt how to solve optimization problems. Okay, now x1 x2 is greater than equal to 0, right? So here we created lower bound as a 0. Let me remove this and show you, and I'm going to run. So lower bound is 0 0 0 and upper bound is infinity infinity 1, because we don't have here upper bound. x1 x2 is only given, so third one is always we have to provide 1, which is the integer. Okay, now there we are using len prog function. Here we use int len prog. Int means integer, len means linear, prog means programming. This is a short name, integer linear programming, int len prog function. And which parameter is integer? A matrix, B matrix, A equivalent, B equivalent, lower bound and upper bound. Perfect. When execute this, and okay, something I forgot to execute. Let me run this again. So here we have, this. So you see that this is the x1 value, this is the x2 value, and you see that x3 is integer as a 1, right? So here we provided upper limit 1, that's why we are getting 1. You can provide 5 6 whatever you have integer values, you can provide the maximum value also. Perfect. And in the same, here I want one more output. Let's say that FVAL, and I'm going to run this again. So it's showing FVL is what? That is the minimum value of that function. At x1 is equal to 0, at x2 is equal to 5, and at x1 is equal to, sorry, x3 is equal to 1. This is the function value, that is minus 12. Okay, we will switch again in PPT. So here, now nonlinear least square methods, it is used for the curve fitting. So two ways we can fit our curve using optimization. First is solve nonlinear curve fitting, that is called data fitting problems in least square sense. Second is solve nonlinear least squares, nonlinear data fitting. So this is the nonlinear curve fitting, that is called data fitting, and it is called the nonlinear data fitting. So two ways. This is the function, objective function, which we write like this. Okay. So in this case, we use nonlinear least square method curve fit. Here you use least square method nonlinear fit. Okay. So two ways we can do it. So I am switching here. Let's see first one. So first of all, you will have your own data. I am creating my data. First of all, let me clear everything from here and let me execute. First of all, I have some data which I have to create a mathematical equation. In previous session, we used the curve fitting app to fit that, right? Here we are using this optimization. This is the X data, means this is the input, or you may say these are the predictors, and we have output for every input here. Perfect. I am switching here. So once we have this data, define the lower and upper bound. If you have like I told in the case of voltage, if your circuit works between 0 to 240 volts, you can't provide more than 240 volts. You have to provide the inequalities for that, right? This is the linear inequalities for that. Lower bound 0, -2, upper bound is this, and this is the objective function. So this is the function handle which I was talking about. So how to create a function handle, let me explain here. I am going to create a single line function here. Z is equal to @, we use @ as a function handle. x y, and I'm going to write the equation square root of x plus y, sorry, bracket here. See, if I have a error, MATLAB will say this, saying that invalid expression, because instead of open parenthesis I used 9, right? So this is a single line function. Is sqrt is a square root of x plus y. So if I provide two inputs, let's say 4 and 5, it will be added and then it will take the square root, that is 4 plus 5 9, that is 3. So single line objective function you can create using the function handle. So in this case, x is the input, x data is the input, and x1 and x2 are the parameters which we have to estimate. Okay. So you can create a objective function like this also. Let's say y is equal to x. Same function I am going to create. Okay. X and square root of x1 plus x2. Say, sorry, again I forgot the bracket there. Just wait a minute. Okay, just 1 minute. Let me clear everything and write it again. This was the function. Here we have to provide the at the rate. At the rate. Let me clear and write it again. Okay, so it will be more visible. Okay, at the rate, x is the variable here, square root of x1, fine, and I don't require this x, and I don't require this extra bracket here, and the single x1 plus x2 is square root of this, right? Let's run this and we have a single line function. So in this case we'll provide inputs in a square bracket, 4 and 5, let's say I'm giving, and let's say that what is the output, 3. The same, this is the first way which we are providing input argument. The before which I created it was like this. So say two ways you can create it. Okay, I'm switching here. So this is my function which I created, and this is the initial guess. In this case we have to provide the initial guess also, that from where it will start. So here least square quadratic curve fitting function, this is the initial guess for x1 and x2. It will start finding the minimum value from 1 by 2 x1 and minus 2 x2. X data or numeric data which we have, y data numeric data which we have, a lower bound and upper bound which we created above. So when I run this, okay, I forgot to execute this one. So first let me execute this one and then this one. Okay, somewhere this also we missed it. Just wait a minute. Let me clear all output and run section by section. Okay, we executed all sections, right? So here we have this optimized value of x1 and x2. So one thing you have to remember, you will have parameters like x y z, something like the x y z or p q r s, something like that. So you have to write as a x1 x2 in this form, x1 x2, x will be become x1, y will be x2, and z will become x3. So you have to write your equation in MATLAB like this. Okay, and this is my objective function here which we have. I mean optimize parameter value of x1 and x2. So this is the another way what we can do. Let me close this one. Another way how we can do it, same process is there, only function will be changed and our objective function will be changed in this case. See what we are doing, I have xy data, and using the function handle in the form of x we created a objective function minus y. So what we are doing here, this is the my equation which I want, okay, and the parameters I want to estimate from this equation, that is x1 and x2, and minus y, this is the observed value. Y will be a observed value, numeric data. So we are optimizing this error function. So if error is 0, means we have a perfect fitting, right? So let me execute all this one by one. And here we have a lower bound, upper bound for x1 and x2, and this is the initial start point from 1 by 2 x1, and for x2 it is 0 start point, and we use this function nonlinear. Okay, so once we run this, we will get the optimized solution. This is for the x1 value and this is for the x2 value. You can plot it also if you want. You can plot here and you can check. So you see that the blue one is fitted one, and the red one which you see, that is the observed one. So observed one, already we had that data, and after fitting this with this mathematical equation which we created above, so this red one is there. So till now we saw problem based, solver based. Right now which we are saying everything, that is the solver based. Let's see more advanced what we can do. We can minimize the multi-objective functions also. Let's say that I have multiple functions like this. Multiple functions, f1, f2, f3, f4, f5. In a single line command, I want to optimize this kind of multiple functions. So two ways we have functions in build, that is f minimax and this f goal attain. Based on the goal, you can use this, or you can use f minimax for that. Okay, simply we use f minimax, and this is the function handle to call the function, and x0. Before that, I will show you some other optimization techniques also, what more optimization you can do with that. Okay, let me show you some equation solvers. Okay, let's say I have one function as a sine, and this is my initial point, something 3. I want to find out where this sine is 0 near around 3. Means this is my objective function. We are calling as a function here. What is at the rate sign here? Let me tell you. First of all, okay, if I give some values here, a is equal to sine pi, I will get some value, right? If I type API, I will get error because a is not a sine, right? I want to make it a as a function, means I am giving the sine function handle to a. So what will I do? A is equal to at the rate sine. Now a will act as a sine. See, now a is acting at the sine, so I am handling the function to that character value. So same thing, I have a function as a sine fun. This is the initial point, f0 function, and this initial point. When I run this, let's see what we are getting here. See, x is 3.14, right? And that is 0. If I provide inside x, that is 0. 1.2246 into 10 to the power minus 16, that is almost 0, right? So if you have to solve any equation, quadratic, it can be any kind of polynomial, we use f0 for that. Or if you have a function like this, just wait a minute. If you have a function like this, this one, cos. Okay, here I want to find out the optimized solution between 1 and 2. This is the initial interval. Before only single value, initial point a single value where it will find out. I want to find out between 1 and 2 where this cos function is 0. So same f0 function and the initial interval for that. So when I run this section and you see that x is 1.5, that is between 1 to 2, right? and this is the value where this function is 0. I mean, the function value is 6.12. 10 to the power, e is 10 here in MATLAB, so 10 to the power minus 16. So between 1 to 2, the x value will be this, and the function value is this, the minimum value between 1 to 2. Perfect. Okay, if you have to find out the root of a system like this, let's say, see, this is a non-linear equation. Manually, if you solve for x1 and x2, see, this is the first equation in the form of exponential, this is the second equation in the form of exponential, and there is two variables, x1 and x2. Manually, if you solve this, it will take a long time, right? So if you have this kind of system equation, to solve this system, like you solve equation like a1x plus b1y is equal to c1, then a2x plus b2y is equal to c2, right? Same kind of equation, that is linear. This is the non-linear equation. So write your equation as a user defined function like before we saw. This is the function f1, this is the first function, f2, this is the second function. This is the way how we write in a MATLAB. And next step is to execute. So what in this case, this is a function, user defined function. So I am giving the handle of this function to fun using @. Perfect. Okay, this is the initial point for x1 and x2, and then f solve. To get the zeros, we are using f0, and where two equations are where they will cut, for that we are using f solve, or to solve the system equation. So when I run this section, so from here there is an option to run this section. This is a script file actually. So if I switch here, now you see that we got the equation is solved. So we got the value of x1 and x2, right? That is pretty simple. So in a single line, in a second, you can solve this kind of linear equation instead of writing manually everything, right? Okay, some more optimization. Directly using function handle, you can write equation inside f min con. It use function initial value a. If you have equalities and inequalities, provide that, then lower bound and upper bound. This is the function. And if you want to explore more, just right click, you can go in the help, and from here you can explore more. If you have a equivalent, b equivalent, provide, otherwise you can leave it, right? Okay, so you can write in a single line also like this. So two value we will get, x value means x1 x2 value, and minimum value of my function I will get. So let me switch here, and you see that this is the x1 value, this is the x2 value, and this is the minimized value of the function, minimum value of the function. Also you can provide the optim option. We are going to use f min con. Algorithm, we are going to use interior point. In this case, see, I am showing you all the way how you can do it. You can define your user function also, user defined function like this. It has to be in a current directory here. See, here I have here, right? Function will look like this, script file will look like this. So this is the function, these are the functions, user defined functions. So we have this function here. A is the constant, x is the parameter which we have to estimate. So x is x1 and x2, and a1 is the constant. So this function we have to optimize. So here if you don't provide optim option, it will take a default algorithm, whatever default algorithm is there. Then f min con, objective function we are calling, and whatever here you see we have a inequality also here, non-linear inequality. If I open this, you can write inequality as a user defined function also. See what is the equality, how it will be. It will be a2 by x1 minus x2 is smaller than equal to 0. So if you have to write the inequality like this. So it is an inequality. it can be equality also. So it is not equality as we know, so we provided as a blank, and this is the my equality, inequality, non-linear inequality. Okay, and this is the function, and this is the way how we provide. We discussed already above, right? This one, app main call, this is the my user defined function we are calling as a function handle using @ command here. And what parameters do we have, and this is the initial points for that, from where it will start. We don't have any linear inequalities and linear equalities, and we don't have lower bound. We are leaving it as a blank. We have non-linear inequalities already, which we defined, and in the optim option we defined what kind of algorithm we are going to use. When I run this section, I will get x1 x2 value and the function. It is showing the elapsed time, how much time it took to execute this. Perfect. Now about multi-objective function. If you have a multi-objective function, just you have to write it like this, whatever functions you have. So MATLAB optimization support for multi-objective functions also and multivariable functions also. So multivariable functions, it is already x1 x2, it can be x3, it can be x4, multiple variables it can be, and multiple functions also it can be. So what we have to do, we have to find out the x1 and x2 value where all these functions are minimized. So we have 5 functions here. So very simple, f minimax we are going to use, and the function which we created as a user defined, we are calling using @, and this is the initial point from where it will start optimization. For x1 0, and for x2 it is 1. I am going to run, and I am going to check that what is the value. So you see that x1 value is this, x2 value is this, and the all 5 functions minimum values for x1 and x2. This is the first function value, this is the second one, this is third one, this is fourth one, and this is fifth one, minimum value of that function. If you have to find out the maximum, then you have to multiply with -1 in the objective function. Okay. Meanwhile, if you have any questions, just write it there, or you can unmute also, and I can reply that. Have any questions? You can write in the chat box. Any question? No? Okay. I am switching on PPT. So we saw multi-objective optimization, how we can optimize it, right? So it is very important. Any plant, if you are working on industries of anywhere which you are working, optimization is used everywhere. Either you are using machine learning, you can't imagine machine and deep learning without optimization. There also we minimize there. Wherever you are designing some kind of predictive or forecasting model, we always require to minimize. Even if you are using neural network, even if you are using some other machine learning algorithms, like support vector machines is there, regression tree is there, optimization is used everywhere. Without optimization, why it is used? To minimize the error. Okay. Okay, now about the global search. So there are different global optimization techniques in MATLAB. First is global search. What is global search? It is a multi-start heuristic algorithm. So we generate a multiple points. It will start optimization from multiple points. Okay. In global optimization, we have one algorithm that is called pattern search. So how it works? Pattern search, an approach that uses a pattern of search directions around the existing points. Means it always search the patterns. If it is not able to search the patterns in the current point, then it create a different another pattern, then it starts searching in that patterns. It works like this based on the pattern. It doesn't rely on a gradients or work on a smooth and non-smooth problems. It works with the smooth and non-smooth both kind of problems you can use. Particle swarm. uh, Let me give an example of particle swarm. Let's say that there are flocks of birds, they are flying, and let's say that they have to find some destination. You saw flocks of birds, they are flying together, right? They have to find some destination. They are searching some destination, they search some destination, then where they have to go. If one bird will identify, or he is able to, it is able to find the destination. If direction is changed of first bird and he is going to the destination and he found the destination, then remaining all other birds will follow it. Okay, so again here multi points, it is also a multi search point. So a collection of particles moving throughout the region. Particles have velocity and are affected by the other particles in the swarm. As I told that if one bird find, then another will follow. That's why it is written it is affected by the other particles in the swarm. It doesn't rely on the gradients. It works on the smooth and non-smooth problems both. Another is genetic algorithms. So it use the concept of evolutionary biology. I think in first year maybe you will be aware about evolutionary biology, or maybe in intermediate you have studied, right? It starts with the initial generation. It creates the generation of candidate that are tested against the objective function. Subsequent generations evolve from the first through the selection, crossover, and mutation. These are the process: selection, the best, then crossover, then mutation. So this is the concept of the genetic algorithms. Another is simulated annealing. Simulated annealing is a very simple, the way the heated metal is cooled, the algorithm which it follows to be a cold any metal. So it controlled cooling of a metal allow atoms to reline from a random higher energy state to an ordered crystalline globally, that is a lower energy state. So the process from higher energy to lower energy, the flow of the heat, same way simulated annealing works in the MATLAB. Multi-start points. So already we discussed we can give a multi-start point. It support the parallel computing also. Sometimes there are lots of iterations to find out the global maxima and minima. So in that case we can use parallel computing, and parallelly we can start multiple iterations at a time. So if you have a parallel computing, so if you have a course, let's say you have a 6 course in your machine, then 6 iterations will run parallelly. So iterations have to be independent. Okay, so this is the function which you are going to optimize. Okay, after that we will end this session. So we have 6 solvers which we are going to compare. So we will use the particle swarm also, we will use genetic algorithms also, and some other functions also we are going to use algorithms in that case. This is a Restringent equation. So in this figure which you see here, we have multiple maxima and minima. What is our objective? That we have to find out the global minima, and what is the value of x1 and x2. Two things this we have to find out, and we have to compare with different algorithms, that which algorithm will be a best for this objective function. Manually it is very hard to find the maximum or minima, right? So we are going to use the inbuilt algorithms which is available in the MATLAB. So I am switching here. So first of all, this is my function I have written as a user defined function. I am going to execute this. We are going to compare pattern search, genetic algorithm, and particle swarm. So this is my function here, objective. This is the objective function which we have to, we are going to use to find out the minimum and maximum value. So first of all we are going to use the pattern search. So this is the function. This is the initial guess for x1 and x2. Tick means time will start. Talk means end time. It will tell me that how much time it took to execute this. Okay. And here what outputs we are getting. Xp means the value of x1 x2 and the value of the function, the minimum value. Flag, if flag is 1 means it is able to find out the minimum value. And for the pattern search we use the simple function in MATLAB, pattern search, objective function, and the initial point from where it will find out. So I'm going to run this, and you see that here x1 value is this, x2 value is this, and my minimum value is this, and flag is once it was able to find out. Okay, in this case we know that the minimum value is 0 and the x1 and x2 is also 0. So in this case in pattern search x1 is not 0, no, even not near to 0, right? X2 is also not near to 0 and my minimum value is also not near to 0. How many iterations it took? How many iterations it is executed? 48. How many time functions are evaluated? That is 174 times in this case, and total time is taken 1.2000, right? Let's write genetic algorithm. In genetic algorithm we generate the population first of all. Okay, so this is the my objective function, again the same objective function which you are going to use, and this is the start point, and this is the initial population. So always remember what you can generate any population, but your columns will be equal to the number of parameters. In our case we have x2 and x1 and x2, so that's why number of columns are 2 here. Okay, then optim options, genetic algorithm, initial population matrix is this population which we created, so we provided in a optim option. So ZA, this is my objective function. Total number of variables which we have 2, we provided as a 2. We don't have inequalities, equalities, or linear or non-linear, any kind. We don't have lower and upper bound. We left it as a blank. And the option which we created here, we also provided here, right? Perfect. So let me run this and check. Now you see, if I compare with this pattern search, you see that in pattern search x1 x2 was 19 and minus 9. In genetic algorithm you see that somehow it is near to 0, 0.02 and minus 0.01, right? And the minimum value is also somewhere around 0.001. So if I compare for this objective function, genetic algorithm is better than pattern search, because we know that x1 x2 will be 0 and my minimum value is also 0, flag 1. And in this case function count, you say how many times functions are evaluated? 5082 times, right? How many times it is generations are done, that which we are talking about, mutation and all, that is 107 times. And the time taken 1.37 seconds, and in previous one 1.2. Of course function counts are more, so it is taking little more time than pattern search, right? Let's try particle swarm. In particle swarm, okay, what is the RNG here? Let me tell you what is the RNG. It is a random number generator. So what it happens at every iteration, first iteration it will search, then it will use the second iteration to minimize the error and to get the minimum value. So I don't want to change the iterations indexing of that. I want the same random generator all the time. Let me show you like this. If I give a command RAND and random, let's say I'm going to give value 100. This is the random number generator. Okay, let me take a random integer here, random integer generator. So you see that 61 we are getting here as output. It is a random number integer generator. Okay, if I click again, now we are getting 45. If I click again, we are getting 74. I don't want to change this, so I will create one random number generator. Let's say RNG 45. You can provide any numeric value which you can remember, no issue. Okay, now you see whenever I will run, I will get always 99. I am getting always 99 here, see. And now let's let's say that I have multiple iterations. Let's say I want to run for 5 iterations, and I'm going to paste 5 times, right? And I'm going to run this. You see, first value right now which shows 55, 29, 8, 45, 48. When I run this, it is again changed. This I don't want to change actually. That's what I was saying. Again I will generate here RNG. You can give any value, any numeric value. Now it will be not changed whenever I run this first run 29, 154, 966. Again I will run, it will not change. So when you are using independent iterations either in deep learning or optimization, always use this RNG. Okay. Okay, here we were particle swarm. In particle swarm, here is the random number generator default. Tick start time, talk is stop time. It will tell me total elapsed time, and this is my objective function here. And this is a optim option, particle swarm, initial swarm matrix, the same initial population which we created for genetic algorithm, same we are using here in optim option. So particle swarm, this is a function which we are going to use, and you want to know the source code of this function, that this is the inbuilt function, right? In MATLAB, you want to see the source code, just select this, right click and click open. A source code will be opened here. See, these are the MATLAB code which you see here. But you can't modify this source code. If you want to modify, you can save it with a different file name and you can modify this particle swarm code. Fine. Okay, perfect. So far so good, no issue. So particle swarm, this is my objective function. Total number of parameters, variables which we have to find out, that is 2. We don't have any constraints, we left it as a blank, and this option file. Let me run this. If I compare with previous one was 0.02 and 0.1, right? And in the case of particle swarm, you see minus 0.8 into 10 to the power minus 6. You see 0.30 into 10 to the power minus 6. It is almost 0. So if I compare with the genetic algorithm, if I compare with the pattern search, particle swarm is better. You see that minimum value is also near to 0. 1.73 into 10 to the power minus 12. Function count 2300. In genetic, it was 5000. Even it is taking less execution, and execution time is also very small, that is 0.62553 only. So if I compare with respect to time, if I compare with respect to iterations, particle swarm is better than genetic algorithms. Particle swarm is better than pattern search for this objective function. Perfect. Okay, last is surrogate optimization. The same way, here we provide the lower and upper bound. What is the lower bound and upper bound, and just execute this, you will get this here. So it will take a little time. Surrogate takes little time. Last is global search. So it will take time because it takes so many function evolution. That's why it takes time. The last one is global search. Let me explain. This is the objective function. This is the initial guess for the global search. Here we first create a problem. Create optim problem. F main con. What is objective? Okay, it is executed. So the value of x1, x2 is this, which you see right now, and this is my output. Still, if I compare with particle swarm is better than surrogate as well, right? And 200 function counts it took. Okay, I was talking about global search. In global search, we can create an optim problem first. First of all, this is my objective function. This is the start point. These are the start points for x1 and x2. Create a optim problem. F main con. This is the algorithm which we are going to use. What is objective? Property value, and this is the objective function which we created here, right? And x naught. What is the x naught? That is the start point. Create the global search as a structure here, as an object, and run this global search on this problem. Let me repeat it again. This is my objective function. if you are going to use global search. And these are the initial points for x1 and x2. Next step, third step, is to create optim problem. So this is the inbuilt function. When you go in the help of global optimization, you can get help regarding that. So this is the optim problem, and this is my solver which I am going to use. Objective was that rf2 dot 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 means I am going to write in a second line. I am going to complete this in a second line. X naught means initial values, that is start point, that is x0. Already we defined x0. Then we create an object as a global search. Then we use the run command, global search on this problem, and 4 outputs we will get, x1 x2, and this output is the minimum value, that is the objective minimum value. This is the flag. In the same case, if I have to find out the maximum value, I have to multiply with minus. In this case here it will be minus like this. Okay, and if flag is 1, it is able to find out the maximum value, minimum value, and here I will get all parameters of that. So let me run this. All parameters, or you may say all properties, we will get in that case. So I am going to run this. In this case, minus 0.14 into 10 to the power 7 x1, minus 0.14045881 into 10 to the power minus 7 x2, and you see that exactly it is that by output is 0, right? Because we knew that our minimum value is 0 of the objective. Flag is 1, it is able to find out the global maxima. Function count, you see 2350. Fine. So let me summarize. We started from problem based, solver based. The first example which we saw, that was a problem based. Remaining examples which we saw, that all were a solver based. And we started from the local linear programming optimization, then mixed integer linear programming. Then we use the linear least square methods. Then further we use the curve fitting least square method, and further we saw some algorithms of global optimization, some advanced algorithms in that case. Okay, so this was the session for today, and right now if you have any questions, you can write in a chat box and I will reply that. From your side, any questions if you want to ask, I will reply. You don't have any questions? So if you don't have any questions, it means you got everything, or maybe you got nothing. So two answers will be that for if you don't have any questions, right? So if you have any questions, you can ask me. Feel free, you can unmute yourself also and you can ask, no issue.